Log on, tune in, find out. Another good idea from Cambridge.
Hilda from Michigan. Usually talk about fluid gravity duality. Please go.
Hi, so I'm going to talk today about fluid gravity duality at a cutoff surface. Specifically, I'll mostly go over work presented in the two papers listed there with my collaborators, Andy Scherminger and his two students, Irene and Slava, listed in the middle. This was work that we did while I was a postdoc at Harvard, but I've just moved to Michigan, so now I'm from Michigan. Okay, so to start off, I just want to give a little bit of history about fluid gravity duality because our work comes from a long line of previous work that people should be aware of. So first of all, I want to discuss the membrane paradigm. This began with the prescient thesis of Thibault Damour in 1978, so it's been around for quite some time. And the membrane paradigm considered fluctuations of a black hole horizon and later of a stretched horizon, and found that these act like a viscous fluid. They could compute the fluid viscosity. Since I have a stick, I'll go ahead and use it. And they got this 1 over 16 pi g. Of course, one can also easily compute the entropy density. You get a 1 over 4 g. And although he did not do the division, I think we can forgive him that and do the division ourselves to get the eta over s is 1 over 4 pi. So of course, we've heard this eta over s is 1 over 4 pi pretty frequently. And it will come up several times here, and of course our work reproduces that same result too. So a few things about this is that it always, the membrane paradigm approach is always considering fluctuations at the black hole horizon or at a modification of a stretched horizon right around it. And it produces not just the Navier-Stokes equation, but a more complicated thing called the Damour-Navier-Stokes equation. Basically, it has some extra degrees of freedom that are still present. Something that I haven't listed here, but probably should, is that it also has a slight confusion that the bulk viscosity is negative in this formulation. So it gives some intuition that there's some relationship between fluids and gravity, but the relationship is not completely simple. So following the work of the membrane paradigm people many, many years later, specifically in 2001, Paul Castro-Son and Steranitz considered in ADS CFT the hydrodynamics of n equals 4 superheating mils. So basically, this is the modern fluid gravity story. Again, they are able to reproduce this eta over s as 1 over 4 pi. All of the work here is done at ADS spatial infinity, that is at r equals to infinity. To get this result, you need a lot of ingredients. So you need string theory, you want to consider supersymmetric gauge theory, and of course, you're using ADS CFT. So initially, I just want to make a bit of a side comment here. Eta over s equals 1 over 4 pi seem to be a bound on the viscosity to entropy ratio. However, it's possible that you can add higher derivative corrections that break this bound. Whether you can do so more than by a small amount is, at least to me, unclear. But I just want to mention mostly that this eta over s is 1 over 4 pi will show up for us as well. So at this point, let's see if I can find some chalk. At this point, what we have is we have some discussion near a horizon, and then we've got some discussion all the way out at ADS infinity. And what we'll talk about today is about filling in what happens at some places in between. Our first paper was titled A Wilsonian Approach to Fluid Gravity Duality. And when I give this talk now, I put the word Wilsonian in quotes, and I'll discuss why as we come to it. But for now, I just want to give you kind of an overview. So we're going to want to relate solutions of the incompressible Navier-Stokes equation. The incompressibility condition is the one on the left, Navier-Stokes, of course, is the one on the right. So those are the Einstein equation. In order to do so, what we do is we fix a cutoff surface. That's this r equals to rc, or this curved line in the diagram that I'm drawing here of Rindler space. And we're going to consider experiments done there. We have to add a couple of boundary conditions. The boundary conditions are that the induced metric on this on this cutoff surface is flat. And the second condition is that we want the waves to be infalling at r equals to RH. So I've schematically represented it by saying we allow fluctuations that fall into the horizon. What I'm really saying is that we don't want things to have come from the past here. We only want things that are going in. And that will be manifested by insisting that the metric remains regular as you approach the horizon. We don't have log terms, for example. When you do this, of course, since we've set the induced metric to be flat along this cutoff surface, the only degrees of freedom that we're left with there are the extrinsic curvature. And the extrinsic curvature can be written in a language where it's the fluid stress tensor. It gives you the fluid stress tensor. Yes?
How seriously should I take that diagram? I mean, that isn't Schwarzschild.
It's not Schwarzschild, it's Rindler.
Oh, I see. Are you ever?
And that's important. In the first two papers that we wrote, no, but there is follow-up work with one of the students, Irene and Andy, which I'll talk about very briefly later, that does do Schwarzschild. But we're generally thinking that we're working in a very near horizon limit in which the size of the radius of the black hole is unimportant. But yes, there is a modification of this that will allow you Schwarzschild. Our first approach was just in Rindler.
But in your story, you also have ADS. So how does that?
No, we don't actually. We don't need ADS. You can map our story into the ADS over here. It will turn out later that that's possible. But at the moment, you'll notice I didn't even draw what happens out here. And that's because I don't care. I'm not putting any conditions on what occurs outside of our cutoff surface. Really, we're only discussing what happens between the cutoff surface here and the horizon here. So I can fill in this little wedge, and I'm not going to ask questions about what happens outside.
So you will never take that dotted line to the right.
That's right. We don't actually discuss what goes over this way.
No, the.
Oh, right. So our initial hope was to try to fill in here. Now you can actually dress up what we do with a cosmological constant and allow yourself to add an ADS in. It is possible to do that. And importantly, you'll find that our results match the ADS results when you do so. But the basic approach itself doesn't require that. And actually, I think this is a good point to make because one of the strengths of our approach is that you don't need to consider just things that live in ADS. The matching between fluids and gravity is a property of horizons, which of course was known from the membrane paradigm approach. But I just want to emphasize that that's still true in our work here. Okay, any other questions before I move on?
So it's the first statement, the fact that the induced metric is which choice that you've made?
Mm-hmm. That is the major choice that we've made. That's the boundary conditions that we've added. In fact, that's the big difference between our work and the membrane paradigm approach, is we're going to restrict out some degrees of freedom that are in gravity by making that choice, by imposing that boundary condition on a cutoff surface.
And if it's not Ricci flat, that's just the membrane paradigm?
And if it's not Ricci flat, then you can think of it as membrane paradigm, or you can think of it as you'll get Navier-Stokes plus some forcing terms. And the forcing terms take on some particular nature. But just to make a point there, Navier-Stokes plus forcing terms could be pretty much anything, because I haven't said anything about the forcing terms. So in order to get just Navier-Stokes, pure Navier-Stokes with a 0 over here, that's where this condition is coming from, or that's why we impose that condition. Okay, so I want to spend a little bit of time, in addition to imposing these boundary conditions, we also take a limit, and I want to spend a little bit of time discussing why we choose this particular limit, where it comes from. So let's just go back to the pure Navier-Stokes equations and not think about gravity at all for a minute. And let's imagine that I have a solution given by some VI, some velocity vector field, and some P. And now let's rescale the solution in the following way. So you'll notice that I've rescaled V by 1 power of epsilon, P by 2 powers of epsilon, but I've also rescaled the spatial coordinates and the time coordinates by different powers of epsilon. So all the spatial coordinates get 1 power, and the time coordinate gets 2. You can just work out from knowing that V and P solve the original incompressible Navier-Stokes to find out that now VE and PE in the new coordinates solve, again, the Navier-Stokes. So in other words, this is a scaling symmetry of the equations. To produce the hydrodynamic limit, what we're going to do is we're going to take epsilon to 0. A couple of things to notice about that. If you imagine that actually V and P was a solution to Navier-Stokes plus some correction terms, those correction terms will go away as you take this limit where epsilon goes to 0. So in other words, this is the particular limit where you start with V and P as some solution to Navier-Stokes plus small corrections, and this limit washes out all of those corrections and induces incompressibility. So you'll find that you get just incompressibility plus the pure Navier-Stokes with nothing left. There's a reason this is called the hydrodynamic limit. Another comment about this limit that's important is that the limit itself is intrinsically non-relativistic. We don't scale space and time in the same way. And that's important to remember because sometimes people ask, okay, well, you're starting with a relativistic setup. You're just starting with general relativity. How did you get something out that's non-relativistic? Well, the simple way to think of that is we put it in by hand. We were doing a scaling of this nature. And so it's not a surprise that we get non-relativistic fluid dynamics. There is work, by the way, a lot of it in this ADS approach, where they effectively don't take such a limit and they can get relativistic fluid dynamics instead. Okay, so we're going to want to think about this hydrodynamic limit. And let me just go ahead and put the metric that we'll be discussing up there for you. And once we have it up there, I can talk about where the pieces of it come from. But first of all, let's check and make sure that this metric that I'm going to propose matches with the conditions that I've already told you we wanted. So first of all, on the top line here, we have the background. And this is just Rindler space in ingoing Eddington-Finkelstein coordinates, which are a particularly nice set of coordinates for this problem. We can check that the induced metric at the cutoff is flat. The cutoff is RC here. So all terms of this form are going to just vanish. And then, of course, because it's a constant R surface, the cutoff surface is a constant R surface, we're going to lose any dr pieces when we go to the induced metric. So the induced metric is really just this plus this, and so it's clearly flat at R equals RC. So it satisfies our boundary condition there, and then we also see there aren't any singularities as you go towards the horizon at R equals to 0. So this satisfies our boundary conditions. So a metric of this form could be the thing that we're interested in. We'll have to check, and we'll do so on the next page, that this solves the Einstein vacuum equations. But first, there's a couple of other things I wanted to point out. The first of which is that you'll notice the V here scales like 1 power of epsilon, so this rho is supposed to scale like a single power of epsilon. V squared and P scale like 2 powers of epsilon, and single derivatives, spatial derivatives, this is supposed to be just the spatial Laplacian, scale like 1 power of epsilon, so this is the epsilon cubed rho. So we've got 0 powers of epsilon, 1, 2, and then 3. The reason the dots are on this line, by the way, is that I actually haven't written correction terms that you could write down, other correction terms that order epsilon cubed. And there are plenty that you can write, but they don't actually affect the, they won't change the Navier-Stokes equation, and they won't change whether or not we can solve the Einstein vacuum equations at this order. Of course, if you wanted to continue the procedure to higher order, you'll get corrections to this. Okay, let me see if there's anything else I wanted to point out on this page. Oh, I just wanted to take 1 minute to kind of explain a little bit about where we got this from, because according to you, we got this from I turned the page on the transparency. And I'll get to your question in just a sec. So basically, if you wanted to derive this, the easiest thing to start with is to start with the idea that a constant fluid should just be a transformation of your coordinates. A constant fluid should be, imagine that you just set one coordinate to be moving, look like it's moving with respect to the other, you get some constant v. From that, you can find what the terms are that look like this here, and actually you can find this term as well. And then when you allow that v to have some small variation, in space and time, then you can calculate what you need to add, and that's how you can find terms of this nature. Finding the pressure terms is a little bit more complicated. It basically involves allowing the size of the horizon to fluctuate, but you can do them by a similar procedure. I think they'd be harder to just guess. And we should also, or I should also comment that, of course, even though one can get it from this procedure, we were also inspired heavily by prior work. Iqbal and Liu and Shiraz Benwala and company, and many other people had been working in this direction before we actually wrote down our particular proposal. And I can talk about the differences between our proposal and theirs later. There was a question.
Yeah, I was wondering to what extent that method implies uniqueness with the metric.
So, from what I've shown you here, that's not it's not obvious that this would be unique. I actually think the right way to answer your question about how unique this is to look at the work that was done. Actually, I have the paper right here, so I can just read off the names. It's Compara, McFadden, Skinderis, and Taylor, an Amsterdam group that put out essentially a way to take this and extend it to all orders in epsilon. And they actually did the calculations up through epsilon to the fifth or something. And in their work, they also discuss precisely how you've made various gauge choices in your coordinates. For example, you'll notice there's no dr squared terms, and it's possible to just put that in as a condition. And then additionally, the form of the dr dx and dr dt terms you can fix. And once you fix that form, I think you have actually removed all of the freedom, and that should be all that's left. Now, one could ask the philosophical question of, okay, this may be the unique metric in around Rindler space as a background with our particular boundary conditions, where you can define a VNP that solves the Navier-Stokes equation. But it's possible you could find the Navier-Stokes equation as embedded in GR in many, many different ways. There's no reason to think that this is the only way you can do it. I think that this is all you can get with our particular formulation. Okay. Let's check and see if this actually satisfies the Einstein equations. Of course, I won't do all the algebra for you, but I want to talk about how it goes. So, the metric on the previous page, you can check it satisfies the constraint equations on the cutoff surface through order epsilon squared, as long as the velocity field that you've written down is incompressible. And then if you write the constraint equation at one higher order, what you find is the Navier-Stokes equation. When you first write this down, you actually don't have a specified value for eta bar. The specified value for eta bar comes when you try to integrate the solution towards the horizon and you insist that there's no singular terms. That's how we get the particular value that eta bar has to be RC. If you tried to start with a metric on your cutoff surface where you solve the Navier-Stokes equation but with some other value for the viscosity, what you'd find when you try to integrate in towards the horizon is that you get log terms that blow up before you get there. So this condition is regularity at the horizon, really. A comment I want to make about the bars that, I don't know if you can tell, but I added those in by hand after I first wrote this talk. And the reason why is, although we called it eta in our paper, it's usually called nu by fluid people because it's a kinematical viscosity. So if you ever try to talk to fluid friends about this, you want to make that distinction clear. The other reason it's important is that if you just naively take this RC and try to plug it into the eta over S formula, it won't work right. You want to make sure that you actually use eta and not eta bar. So you have to be careful about that.
What's the difference between kinematical viscosity and ordinary viscosity?
It's just a scale. In the incompressible case anyways. I'm not sure about the more complicated case. So it's just a matter of where you've put your other factors.
Are you saying I can remove it? I mean, effectively. You're saying it just gives you the scale of the problem, and then I can just, through picking some sort of function, remove it from the Navier-Stokes equation?
You can't actually, because the only way that you'd try to remove it is by rescaling effectively the Reynolds number. There we are. And that's set by both your epsilon scale and the eta bar. And you can't really, that's actually a number that you can't get rid of.
Yes.
So you can hide it by scaling epsilon, use half epsilon instead, and it would look different.
Sorry, I have a really stupid question. I thought the Reynolds number was a property not just of the fluid, but of an object moving through the fluid.
It is, it is because it's about the scale of the solution, which is built up by the size of, say, an object moving through it. So if the object you're moving through the fluid has a characteristic size L, that's one of the components that goes into the Reynolds number. And here, we don't have objects moving through the fluid, although if any of you are wanting to introduce them, maybe it's possible to do so. What we have instead is the scale epsilon that tells us the characteristic length scale of our solution of the particular V that we're working with. So essentially, you can take that epsilon and put it in for L. Okay, so now we've actually gone ahead and satisfied our constraint equations through the order that I'm going to try to do today. But we also want to check that we satisfy the rest of the Einstein equations. In other words, we also need to make sure that we can satisfy the R components and that we can continue to satisfy the constraint equations as we move towards R goes to 0. So you can just compute this. And you actually find that, I think, talk in our second paper a little bit about needing to add some corrections at higher orders in order to satisfy this through epsilon to the fourth, but those corrections don't affect what happens here. Of course, what we've written so far is we've written through order epsilon squared, you get this, at epsilon cubed, you get something like this. If you keep writing these down, you will get corrections at higher orders. And as I said before, that was done in the paper by the Amsterdam group. So far I've been talking entirely about the hydrodynamic limit. But we usually talk about two limits in this problem, either the hydrodynamic limit or a near horizon limit. So I mentioned earlier that one of the reasons you can't see a Schwarzschild radius here is that we like to think of ourselves as being in some very near horizon limit where only the behavior of the horizon itself is important and we can think of it as flat. And what I want to show you in the next couple of transparencies is actually that these two limits are related to each other. So specifically, let's rescale our coordinates. So I'm going to rescale x by some RC over epsilon. Tau, again, by a different power of epsilon. And then I'm just going to use an r hat so that the cutoff is now at r hat equals to 1. And then if I rescale the metric overall, so I'm just going to pull out some epsilon squared over RC squared factor, then I can define some lambda as the particular combination of epsilon and RC given there. And although it's not immediately obvious, you can just take the metric from a few pages ago and rewrite it in these hatted coordinates, and you get the following. Just to kind of point out a few things for you. The epsilon to the 0 terms that were Rindler space have now become 1 over lambda terms and 2 terms that are power lambda to the 0. And similarly, we've moved around some of the terms. This was an epsilon to the first power term. Now it's a lambda to the 0 power. This was epsilon squared. It's also lambda to the 0. So we've apparently mixed which terms are which in the expansion. But actually what we've really done is we've made explicit the dependence on epsilon. So I was commenting earlier that, for example, the Reynolds number is kind of hidden because you have to think about the scale epsilon that we've put into it. This is taking that out and making it explicit. All you're left with is lambda. Another way to think about that is that I haven't, since I've explicitly rescaled my V and the coordinates by the appropriate powers of epsilon, I don't need to think of these V hat and P hat as having any particular scaling anymore. The scaling's all written out. So only lambda is left. Importantly, there aren't weird other combinations of epsilon and RC here. It's only the combination epsilon squared over RC that controls the expansion now, which makes us think that perhaps it's the only important quantity. So let's forget starting with the approach that we've done with the hydrodynamic expansion. And instead, we'll just start over and we'll consider a Rindler wedge with the boundary at r equals to 1. And then we've rescaled it in the following way, so I can write it in these coordinates. So for small v, we actually found the linearized solution in our first paper. I should make sort of a comment that if you guys are interested in reading these papers just as orientation, our first paper is entirely linearized, where we actually do the full nonlinear Navier-Stokes equation is in the second paper. But similarly to the way that I talked about how we derived the hydrodynamic approach, you can take our linearized solution and you can work out what correction terms you'd need to make it nonlinear. And you find the following here. And this should look really familiar. In fact, modulo this term here, it's exactly the same. This term is a higher order correction term that you can see more easily in the hydrodynamic limit. To see that it's higher order, you would have to go and unscale it again. So basically what we found is we found that taking the hydrodynamic limit, starting at whatever cutoff surface you would like, is the same as taking a near horizon limit where you've pushed your cutoff surface to be close to the horizon. And specifically what we're actually doing is we're taking small lambda, and you can work out that small lambda is the same thing as taking the proper distance to the horizon to be small. So conceptually, we can kind of think about this as, in the hydrodynamic case, when I ask, so hydrodynamically, we'll forget about the ADS. Hydrodynamically, I can be some large distance away from the horizon, but then I'm assuming that the solution, that the perturbation that I'm considering, the velocity solution, and its derivatives are small. If I wanted instead to consider an arbitrary solution, well, then I have to push it closer to the horizon until relative to how far away I am, they're small. So it's actually really just one limit. Another way to make this statement is that if you didn't want to derive the hydrodynamic expansion by considering just the fluid equation itself, you could instead start with a natural near horizon expansion, and you find that you get out the hydrodynamic expansion. So I want to make a couple of highlights here. As was commented before, one of the nice things about our approach is that you actually don't care about the ADS at all, because everything we're doing is in between our cutoff surface and the horizon. And in the long wavelength limit, this will work at any cutoff surface that you're interested in. As I just said, of course, the farther away you are, the more your long wavelength limit has to be, the stronger it has to be. But you can still do it at any radius. Yes?
So if I wanted to do ADS,
right,
wouldn't I want to foliate by sphere for my surface stuff?
Actually, you could. I don't think that you need to set up with spheres. I think you can still just consider the flat limit, very, yeah. And what you need to do is you need to dress up your equations with the cosmological constant. So we're, of course, working in the vacuum case where that's 0. And so you'll get a slightly different format for the metric. It actually looks very similar to what both Iqbal and Liu and Shiraz and company had written down.
So your bulk metrics are Ricci flat?
The book, yeah, because they're all solutions of the vacuum equation. Let me add one caveat to that. They're all solutions of the vacuum equation when we tried to do the nonlinear setup. Actually, in our linear paper, we did consider adding p-form matter if you'd like. And you can end up with a similar setup. But there, of course, you have to be a little bit careful because what I've said is that we start with a cutoff surface and then we do experiments there, by which I mean we kick the extrinsic curvature. And you have to be careful that all you're kicking is the extrinsic curvature and not the flux. So here it's actually totally clear because the only thing we have left if we impose this boundary condition is the extrinsic curvature. It's the only thing we could possibly have kicked. Okay, as I was just saying, we could either take long wavelength limit at some large RC, or we can take RC small, and then we don't have to worry about taking the long wavelength limit to be long, because everything is long when you're close to the horizon. And one thing I want to point out that's more obvious from our first paper is that physical quantities, like, for example, the diffusion constant, actually turns out they have a local definition on RC that didn't have to be true. It might have been the case that you needed to integrate some function all the way between the two, and it turns out you don't, actually. It's given in terms of things that you already know just at the cutoff surface. And something that we found a hint of in our second paper was that maybe the space-time could be algebraically special. So let me talk a bit more about that. This is a concept of Petrov type. So spacetimes are algebraically special or of higher Petrov type if they have principal null vectors that coincide. What this corresponds to is certain null projections of the Weil tensor vanishing. Essentially what we can think about it as is if a spacetime is algebraically special, it's got some sort of alignment of its null vectors. So for example, Petrov type 2, I'm writing this down just in 4 dimensions because that's actually all we did in our initial paper. I should point out actually that everything else I have said up to this point is whatever number of dimensions you would like. Although as a caveat, in 3 dimensions, fluids are boring because 3-dimensional space-time corresponds to a 1 plus 1 dimensional fluid, and di, vi in 1 dimension means that you only have constant things. So there isn't anything interesting for us in less than 4 dimensions. Okay, so in 4 dimensions, I could write down, for example, this is the condition that there exists a real null vector k which satisfies this contraction with the Weil tensor being 0, is the condition that a spacetime is Petrov type 2. A little bit of an aside before I continue about why you might care about Petrov type. It's useful for finding exact solutions to Einstein equations. And it's also something that if you want to talk to GR people, they like to think in terms of Petrov type. There's also some very nice theorems relating Petrov type to the existence of various null congruences and so forth. So if we want to discuss being able to solve Einstein equations, for example, if I wanted to imagine in some wonderful world that our work is relatable to, say, cosmic censorship or existence of singularities and so forth, which I should say I think Andy's original hope was that maybe we could do some relationship between that and existence and uniqueness in Navier-Stokes. I think that's perhaps a bit optimistic because our approach is inherently perturbative. But regardless, if one wanted to make such a relationship, thinking about things like Petrov type might be a good direction to go because it is useful when you talk about such theorems in GR. Okay. So we were able to calculate in 4 dimensions in our nonlinear case, and this is our second paper, that the fluid dual spacetimes I wrote down for you earlier, it turns out they're Petrov type 2 through 14th order. Now that sounds like a heck of a lot, it's actually not. The invariant we calculated, you can show that it has to be 0 at least through 12th order, so we've only shown that the 2 higher orders are 0. But it's still something perhaps interesting. And then in further work, Slava and Andy examined what happens when you try to put the condition of Petrov type 1 on the spacetime at the cutoff surface instead of having the infalling conditions at the horizon. So essentially what their setup is start at some cutoff surface, impose that the induced metric should be flat there, and then additionally impose that there's a particular real null vector that contracts with the Weil tensor to give 0, and attempt to integrate this in. So in this paper, they showed that this works at lowest orders when you impose the condition at the cutoff surface, and it can replace needing the infalling condition at the horizon. But it does turn out that there's some complication when you attempt to impose the Petrov condition throughout the spacetime. So normally we think of a spacetime as being Petrov, and that's just a statement I make about the spacetime as a whole. But of course, this is a quantity you can calculate locally. And so you could say that, locally it's true, but it doesn't necessarily continue everywhere. I should also point out that if you take the approach of the Amsterdam group and work out what happens to all higher orders, it is not the case that it stays Petrov at higher orders. So one might imagine that you need to make some change in the cutoff condition at higher orders if you wanted to continue to impose this condition. Okay. And then somebody asked earlier about the Schwarzschild case. And it's a good question. So in fact, Irene and Andy have written a paper about this. It turns out they need to consider a slightly different set of boundary conditions. Not just do they want to set the induced metric to be the boring metric on a sphere, but additionally they also want to allow it to be just conformally round. So they allow some scale in front. To kill off the extra degree of freedom given by that, instead they fix the trace of the extrinsic curvature to be a particular value here, this 1/2 lambda. And then they continue imposing otherwise the infalling conditions at the horizon just the same way that we did. And you can show that at lowest order, the remaining degrees of freedom, in other words, the non-trace parts of the extrinsic curvature and this rho, can satisfy Navier-Stokes equation on a sphere. And again, this is something that they've done in the same perturbative approach. Here they're only discussing some near horizon limit where lambda is going small. Which you can also see as a large constant curvature limit. Okay, there's a few things that I wanted to point out from our linearized work. As I mentioned earlier, our first paper talks about just the linearized limit and discusses that this is the unique setup with our boundary conditions that you can get there. And then we do the nonlinear embedding in the second paper. And I wanted to mention, first of all, that we found in the linearized case that you can think of the radial evolution of the entropy, which I've written here as, beta is 1 over the temperature, and then you can define an energy, pressure, and volume. And then, of course, I mentioned also in that case that we considered adding matter, so you could add whatever sum of mu's and q's you would like. And you can show that radial evolution of this, where by things like the energy and the pressure, I mean the things that you get out of the fluid. It's just a component of Einstein equation. That's it, just one of the radial components. Actually, a combination of them. We also find that the diffusion constant, so of course at the linearized level, all you get is one constant, because really the linearized equation is just some omega is k squared with some number. That number is the diffusion constant, and you can show that this diffusion constant has to decrease as you increase your radius. In other words, as you move the cutoff surface farther away, you can show that the diffusion constant has to decrease as long as the matter you've put in satisfies the null energy condition. So there appears to be some relationship between the flow of the diffusion constant as you change your radius and the null energy condition. One thing that I want to mention is this D here, we define it precisely in the first paper if you're interested, but there's a relationship between it and eta. So one might hope that the fact that eta actually doesn't seem to flow, you get the same value no matter where you place the cutoff surface. And in fact, if you dress up our equations with lambda and go back out to some ADS, you find again that eta over S does not actually change. That eta over S is relatable to this D in the case where there's no matter. So this matches up with ideas that people who were studying fluids from the ADS-CFT approach had before, that eta over S shouldn't flow as you change what radius you're looking at.
What's the interpretation of the flowing diffusion constant? I have a fluid. What experiment do I do to see that?
I would love to have a better answer for that. So The basic reason I don't is that what we're actually doing here is we're considering different fluids living on different cutoff surfaces. Because if I build one spacetime with the particular cutoff surface flat here, in general, any other cutoff surface I consider will not be flat. And I can't build a Navier-Stokes fluid there because it'll be Navier-Stokes plus some corrections. So what I'm really saying is I consider one cutoff surface and I build some fluid here, and then I consider an entirely separate system where I have a different cutoff surface and I build some fluid there. The diffusion constant for this fluid will differ from the diffusion constant here in that way.
But
So-
given your answer to my previous question, that you could interpret this as somehow an object of a given length scale.
Mm-hmm.
If I think about maybe Brownian motion of an object of a different length scale, is this the diffusion constant that would appear there?
I feel like it must be the same one because there's only, when you're talking about linearized fluids, there's only this one number, this one scale that you actually have, the relationship between some omega and some k squared. You can think of it as the thing that gives you the time scale if you're to perturb the fluid in some sharp way. It's the thing that gives you the time scale over which it spreads out. But I can't really think of this as a flow in the way that we originally wanted to. So one of the things you might hope to get out of this whole story is, hey, I can change the radius, that means I can change the energy scale, because we want to think in terms of ADS CFT. If I can change the energy scale, maybe I can think about what happens in a fluid at different energy scales. But the problem is, or one of the problems with this interpretation, is that it's really a different fluid, because we had to reset up the problem. So our Wilsonian idea, which was essentially that what we've done is we've integrated out everything that happened over here. That's why I was able to erase what happened here, and then we stop at some radius and then ask what happens only inside of that. Well, it isn't really actually what we've done. What we've done is set a boundary condition at a particular location and then integrate it in. So I haven't included what happens above that. Now you could imagine, maybe you can still learn something about this. So something that fluid people do sometimes is represent the effect of higher corrections, shorter wavelength corrections by some forcing terms. And in fact, that's essentially what would happen here if I consider some cutoff surface fluid here, and then I say, well, what happens at some cutoff inside of that? Well, now in general, it's not going to be flat, and what happens when it's not induced metric, it's not flat, you get forcing terms. And maybe those forcing terms might have a form that looks somewhat similar to the way that higher wavelength corrections are included. Shorter wavelength corrections are included. But I can't answer your question about, your original question right now was, how can I test this diffusion constant? Well, I can't test the flow of it because there isn't a physical experiment with a fluid I can do that moves me in radius. Or at least
You're
there's
not
not one we
saying
understand
that
at this
modes of different wavelengths diffuse at different speeds. That's not what the interpretation of this is.
I think that's not what the interpretation is. The interpretation is that when we've picked a particular cutoff surface and we consider all modes which are smaller than the epsilon that we need to be in a valid perturbation limit there, then they all have this same diffusion. But if I built it if I had some fluid solution and I wanted to build a gravity dual to it and that fluid solution wasn't small enough to be at that radius, then I'd have to build it at a larger radius, and then I'd find.
Sorry,
Yeah.
just to be comment, but is it somewhat analogous to saying it's setting some kind of RG scale? It's just like specifying mu. Not physically meaningful in any given experiment.
Yeah, that's fair.
You have to move into it and then mu will change accordingly.
Right.
It's not quite that, because then the fluid at one energy scale, meaning at certain wavelengths, would have one diffusion constant, and at a different energy scale would have a different diffusion constant, but that's not the right interpretation.
The other thing I should quickly mention here before we get too far on this aside is that actually this less than or equals to in the vacuum case is equals to. So in the vacuum case, it actually doesn't change. It's only when you allow yourself some mu and some actual matter that you can have a change, which I think is actually a similar statement because that's when you've introduced some extra scale that you can compare this radial scale to. Whereas in the setup that we have here, there is only the one, there's one number, there's no scale to compare it to. Okay, so let me move on and talk about forcing solutions. This is something we actually did in our second paper, but we were only able to do it at the linearized level, so it's in the linearized chunk of the talk. And what I've done here is I've written down slight variation on our previous metric. So all of this part looks very similar, and then I've added some extra terms. What do these do? Well, essentially, the way we're setting this up is that the forcing term here and these alphas and etc. are set up so that this is just pure Rindler space before the time tau equals tau star. And then after the time tau equals to tau star, there's the fluid solution with the V and the P, which I haven't written down because it's only linearized, that's right. So there's a fluid solution with just V. So what we're trying to do here is we're trying to say, imagine that I start with flat Rindler space and then I kick it. And you might think of kicking it as sending in some null wave here. And then afterwards, I want to watch it diffuse. So this is me trying to actually do one of the experiments that I was talking about at the cutoff surface. I send in some null wave, it perturbs the cutoff surface. Now I maintain that the cutoff, I consider only those solutions so that I can maintain that the cutoff surface has induced metric being flat. And this satisfies that. You can quickly check that that's true. And then I find, as you might expect, that at least at linearized level, this follows the Navier-Stokes equations that we would expect. So a couple of points that I want to make about this. The main reason we didn't do this at the nonlinear level is that we've already cheated a little bit because I'm allowing a delta function in the metric. We don't usually do that. We don't really know exactly what it means physically. We tend to think about delta functions being present in the curvature, and the metric's only allowed to have things like theta functions in it. So trying to make that make sense at the nonlinear level is challenging, and we weren't able to do it. The second thing is that I wanted to mention why we're considering this in the first place. So as we've just been discussing, Navier-Stokes is diffusive. So if I start with a sharp solution and then watch it over time, it spreads out. But of course the reverse is true. If I start with a nice spread out, relatively smooth solution and follow it backwards in time, then it might blow up. And so we're going to find that if I tried to start with some nice solution down here and then I wanted to keep following it backwards and backwards and find out what happened in the past, in general I'm going to wander out of my hydrodynamic limit. And I'm not going to understand what's going on with the fluid. I'm not going to trust the perturbation. So we wanted to show that, at least in some way, it's possible to kind of cut things off at some scale, where at some point in time where we still trust what happens. But of course, as I said, we were only able to do this at the linearized level. Oh, and I should mention one more thing, which is that we've talked a couple of times about how breaking the boundary condition that the cutoff surface is flat at a particular point is equivalent to adding a forcing term, and that's actually exactly what we've done here. So if you work out what the actual equation that V has to solve here is, you get something like Navier-Stokes plus this forcing correction, so it's forced at some delta function in time. And sure enough, if you work out what this metric is, it's not flat. The induced metric is not flat, just at that point in time, and then it's flat again. Okay. So, since I'm getting relatively close to out of time, I'm going to do some conclusions, and then I'm going to cheat by adding an extra slide afterwards. So, first of all, the conclusion.
Question about forcing terms. Can you try other things that are smoother forcing functions?
So, we actually did. This is one of the things I have to admit I'm least satisfied with about our paper, because we did spend a fair amount of time trying to write down something along the lines of like a Barabas-Israel matching condition across this null surface. And we were unable to find a way to do so in our perturbative approach that made sense. That doesn't mean it's not possible, and it's actually something I still think about from time to time. If any of you are seriously interested in that problem, you should come talk to me about it. This was basically what ended up that we could actually make somewhat rigorous and was fit to publish. But yes, I would very much like that to be true. I'd like there to be some smoother behavior, smooth in the sense that there's still something, singular happening at the null surface, but it's the kind of singular that we're okay with, as opposed to this annoying delta function.
What is the point of this delta function? I mean, physically, what does it mean?
It doesn't mean anything.
And nothing happens again.
Yeah, so physically what it's supposed to represent, you'd really think of it more as some kind of thin Gaussian behavior. What it's supposed to represent is I've kicked the fluid at some particular point in time. I sent something in, it kicked the fluid, and then I stopped the forcing, and I watched what happened afterwards. So it's really supposed to represent that on this red line, I break the boundary conditions, it's not flat, the fluid is forced, and then afterwards I can watch it go away.
Boundary conditions at RC.
That's right. The boundary condition at RC and tau equals tau star is it's not flat. It's broken. And that's in order to add the forcing. But in terms of what it means physically, as far as what did you actually do in this solution, I don't think there is a good physical interpretation for a delta function in the metric. So what there is, basically what you could think of is maybe we've got the wrong coordinates on one side of this boundary, and if we change the coordinates in some nice way, we could see that maybe there's a smooth solution underlying it that has only theta function behavior, and we might hope that there's some way to make this smooth, as David was talking about.
I mean, if you replace the delta function with some Gaussian or Lorentzian or something, and then parameter controlling its width, etc.
The problem is controlling the expansion, this is also why we're only able to do this at the linearized level, because you have some width for that Gaussian, and you want it to be small if you want to think about it as something that's happening for a short time. But if it's small, then, I don't have a good picture of it, then the hydrodynamic expansion is bad. Because we want V to vary slowly in time, as well as...
That's just the limit of taking
exactly.
small, so your
Yes.
approximation's bad there.
I agree. And I think this is more of a sketch of where one might want to go with this than an actual proof of it working. I agree. You could imagine doing some sort of double expansion where you consider the limit where the Gaussian gets small, but the wavelength of the things that happen afterwards is still long.
Yeah.
But I agree, it's worrisome.
You don't get derivatives of delta function in the region of curvature, or?
You would. That's why we can't do this at the nonlinear level, which is why one would hope that this can be done in a more smooth way so that it's actually physically meaningful and comprehensible. But we have not at this stage been able to do so. Okay, so let me go back to the conclusions page. What have we done today? So what we showed is that it's possible to embed any solution in Navier-Stokes. I should make sure to point out that I mean any hydrodynamically expandable solution of Navier-Stokes. I can embed it as data on some flat hypersurface in a solution of Einstein equations. Said the other way around, I can start with solutions of Einstein equations, add in the boundary conditions that we impose, both the one at the horizon, that it be only infalling, and the one at the cutoff surface, that it be induced metric being flat. Einstein equations plus those boundary conditions plus either the hydrodynamic or near horizon limit corresponds one-to-one with solutions of incompressible Navier-Stokes. So to be precise, what I'm saying is there's some large parameter space that's the solutions, all the solutions of Einstein equations. If we impose our boundary conditions on top of that, then we find the solution space for Navier-Stokes. So our near horizon limit is providing a precise mathematical sense in which horizons are incompressible fluids. I should also point out that this approach is asymptotic agnostic. I haven't said anything about what happens outside of this cutoff surface. Well, I said a little bit that it is possible to dress this up with a cosmological constant and map it onto the ADS CFT story. Yes?
You said it shows that the horizons are incompressible, but it sort of shows that any surfaces are.
Not quite, because we really do need to be on top of Rindler space here. And I would argue that if you're close enough to any horizon, it looks like Rindler space.
But is it just on the R equals RC surface, or can't you put it anywhere?
You can put it anywhere, but then you need to impose the additional condition that it's regular at a horizon. So you need some horizon to impose that condition at. But I actually think that's an interesting question, because certainly initially we start with some Rindler background, and then we add on top of it that we want these induced hypersurfaces to be flat. Could one consider a more general approach where you start with some unknown solution? insist on having some flat hypersurface inside of it, and then ask what happens to perturbations at that hypersurface. And I think you'd find that only those solutions where the flat hypersurface is outside of some horizon gives you fluid behavior. Although I certainly haven't shown that today. Okay, so a couple of things that we could think about the future possibilities. As I briefly mentioned before, one could try to think about both uniqueness and existence on the GR side and the Navier-Stokes side. Perhaps as something a little bit more realistic there, there's tons of things that Navier-Stokes people know about solutions to their equations, and there's tons of things that gravity people know about the solutions to their equations, and maybe they're not all the same things. So we can port them from one side to the other, and I'm not sure which direction I think might be more interesting. Actually, I do have an opinion on that. I think that from the fluid side, they've been working on the problem a lot longer, and so may have more to tell us relativity people than the other way around, but I'd be happy with any sort of transit across it, either way. Some things that we've thought about working on and variously picked up over the past year on and off. One is, you might ask, can I understand the gravity geometry for a particular solution? For example, there are exact vortex solutions that one can write down for Navier-Stokes. It'd be nice to understand the gravity object that's equivalent to those. This is a hard problem for reasons I'm not going to mention right now, but if any of you are interested, we can talk about it again later. Essentially, the difficulty is that a lot of the vortices are singular, and we're not very good at modeling those kinds of solutions. We might want to try forcing at the nonlinear level to make that solution actually make some sense. And something that is part of the dream of this project that I think we still haven't realized, and it would be nice to actually realize, is to make some kind of relationship between energy scales in Navier-Stokes and space-time radius scalings. So, of course, all of these things are kind of related to each other at some level. If we can solve one of the problems, maybe we can solve some of the others. For example, vortices in Navier-Stokes are intimately related with the relationship of how energy moves between different scales there. So if we can understand how those things show up in gravity, we might be able to make some progress on understanding how the space-time radius scaling corresponds to different energy scales. Okay, so now I'm going to cheat and give you one extra slide, which is just a couple of papers that I want to mention that I think are particularly relevant. These are all follow-up papers. This is one I was talking about earlier that does our approach to all orders in epsilon. This is one of the, I think probably the cleanest mapping onto the ADS story. The same thing, sort of the same thing, can also be done for cosmological horizons. And Irene, our collaborator, is also on this paper, as well as a couple of other people who are at Harvard. And then additionally, there is a problem with this scaling limit in that because it's incompressible, we've scaled out the sound modes. So that means we've sent the speed of sound to infinity, but oh wait, there's a speed of light in here too. How do we make the speed of sound greater than the speed of light? And they talk about this problem and find that it's more or less not an issue in Rindler space, but once you consider things like Schwarzschild, you'll have to actually pay attention to how it behaves. In other words, you might also think of this as being some long time limit because, again, Navier-Stokes is dissipative, so if you start out with some funky-looking solution and then wait for a while, eventually it'll be in the hydrodynamic limit, and then we can discuss what's going on. But it's not the very, very long time limit in cases outside of Rindler, because in that case you'd see that the speed of sound looks like it violates causality, and that can't happen. So there's other things you have to consider. Okay. Yeah.
So I was just going to say about that. I mean, the Navier-Stokes isn't relativistic, so.
The Navier-Stokes isn't, but the GR solution is.
Yeah, so when you're taking that hydrodynamic limit, you're taking a non-relativistic limit, surely, because I'm scaling that limit again to scale that
exactly.
in a non-relativistic way.
Exactly, but if you wanted to include all the higher order epsilon corrections, then you do run into this issue. Outside of Rindler space, anyways, you do. And it's really a question, sort of a philosophical question of what you're actually trying to claim. Okay, so I think I have, in fact, run out of slides. I didn't cheat any more than that. That's all I've got.
More questions or comments?
You mentioned about GR solutions and Navier-Stokes solutions and their relation. I was thinking, well, if you have, if you're trying to find some kind of isometry in the GR case, you end up with conditions on the metric which are in a polynomial in R, which is an infinite tower of conditions. Is there some way of perhaps rewriting the metric and so that the V and P can depend upon R?
I haven't really thought about how to do that. I think that essentially what you'd be doing is identifying a different component of the metric as V or P. For example, I've always written out, the polynomial in 1 minus R, and we usually write it as some expansion like that because we want all the terms to go to 0 as R goes to the cutoff. So it's some polynomial in 1 minus R, and if you wanted, rather than considering 1 minus R times V, V is the thing that solves an Navier-Stokes equation, you could imagine that the thing that you're going to consider is 1 minus R times V. And all this is just some raw scale, some number in front of V. So it'd be different at different R, but really just trivially, it would just be a scaling. It's not going to change the actual form of the solution.
Well, I was looking at the Skenderison's paper, and so the way that one thing they do to develop higher orders is to use integrals between R and RC, so those terms wouldn't necessarily disappear.
They have set it so that the cutoffs, that they disappear at the cutoff surface again, because they're still imposing, and that's all I'm saying, is that they just disappear at the cutoff surface, so they're always of some form 1 minus RC times things. But you could have some more complicated polynomial in front of it. Essentially all I'm saying is that the thing that you identify as V is a little bit up to your choice. I'm saying that it's the constraint equation that gives us Navier-Stokes, so you could pick the constraint equation somewhere else if you'd like. In general, the problem there is that it's not actually going to be flat, and so you'll get some forcing terms for the Navier-Stokes. So you can identify V as something different, and maybe you'd get Navier-Stokes there, but then all you've really done is rescale your problem. I don't think you actually get any new information out of that. But if you'd like to talk in more detail about their approach later, I'd be happy to.
So you mentioned that we might have something to learn from fluid people.
Right.
Have you made any progress in that direction, for instance, matching special classes of fluid solutions where properties are known to special geometries?
I've tried. That is the mention here, oops, it's not actually letting me go back. The mention here of vortex solutions was the first place where I was really trying for that. And it turns out that a lot of the exact solutions do actually have singular behavior. Like, for example, the simplest vortex that you could consider is just in 2 dimensions. And if I want it to be asymptotically flat, I'm going to consider the vortex that has some core where it blows up. And the problem is that those solutions don't naturally fit in our paradigm. And one might still hope to make some progress. This is also something I've actually thought a fair amount about, because someone was mentioning isometries that are present there, you might hope to still have to be present in your gravity solution. For example, if I'm considering a solution in Navier-Stokes that is time independent and angular independent, as this particular vortex is, then I would expect to have killing vectors in the time and angular directions, and you do. That's fine. The obstruction is really the behavior as you go towards the core. Or alternatively, if you like the other approach, consider the vortex that scales the other way and blows up far away. And then the problem is I don't understand what happens far away. So something that I haven't tried, but you could imagine trying, is there are things like the Taylor-Green vortex that has, it doesn't have any singularities anywhere, but it does scale in time. So it's a little bit more of a complicated solution, but one might still try to look for that in our case. And the thing that I want to kind of point out about that is that it's easy to write down the lowest order behavior of what happens. That's what we've already done for the general case. The problem is what happens at higher orders. So if you try to continue the solution and actually understand what the gravity object is, not just in perturbation, then that's where it gets difficult. And if one wants to say anything about uniqueness and existence, that's exactly what one is going to need to do. And I would actually argue if one really wants to understand scaling relationships like this too, you need that as well. But that's still not something that we've done so far, something we're still thinking about.
Why is eventually at OS it was 104 pi in both contexts? I thought one of the initial motivations was to understand,
Right.
for instance.
So there's actually 3 contexts, and I'm not sure which 2 you're thinking of.
Three?
Yeah, so the first one is the membrane paradigm.
There was polycast.
Right, okay, and then there's ours.
Wait, oh, you also got.
Yeah, I was thinking of us as a third approach. Sorry. So if you do that, then you can kind of think of, well, I'm allowed to move this R wherever I would like. And so if I move the R close to the horizon, I find that A over S is 1 over 4 pi. I also find in the vacuum solution it doesn't scale as I move R to different radii. And so we think that it shouldn't be different if you're looking at R equals to infinity in ADS. And what I've shown you today doesn't show that because I didn't dress up with the lambda, but you can.
That's right, because your paper, I thought this was the picture until you said that you're never considering ADS.
Right.
You
We
said
don't
that some other paper
we don't
did.
actually keep the lambda in our paper, but if you would like to, it can be done, and you find that the same behavior happens. Lambda
Okay.
doesn't affect the way that A over S.
And apparently this is not affected by having a different theory either, by coupling to other fields, because the n equals 4 computation is not in general relativity.
That's right. So in our linear paper, when we consider P-form matter, we can actually show that for that case, if you've turned off mu, then you still find that it doesn't flow.
There's also this old Iqbal-Liu result that shows that in ADS, you can,
You don't
with zero
expect
momentum
scaling.
limit, it doesn't depend on the radial position, eta over s in particular. Computed at the horizon, computed at the boundary, exactly the same.
And I should also comment about that paper that it is possible to recover much of what we did by taking what they've done and pulling the lambda back out. It looks very similar, I think, in different coordinates, but otherwise.
I just have one question. Can you get magneto hydrodynamics? I mean, by putting in some sort of electric fields and charges and stuff?
Yeah, sure. So if you wanted to consider, rather than just kicking the metric, allow yourself some matter and kick the matter as well, then it should be possible to set up the right matter so that you get both Navier-Stokes and the interaction with electromagnetism. I don't know how useful that would actually be for understanding magnetic hydrodynamic problems because, one of the complaints about this work that I get from people sometimes is that Navier-Stokes is a really complicated nonlinear problem. GR is worse. So how have you gotten anywhere? Well, it's GR with a particular boundary condition, first of all, so it isn't actually as bad as it sounds. But I think the same complaint could be said, maybe even more so there, because GR plus a general matter is pretty bad. So is magnetohydrodynamics, don't get me wrong, but
Okay, then let's thank the speaker again.